All right, let us revisit gradient descent. Right? So this is our loss function, the binary cross entropy loss function. Now, in tutorial 2, we have calculated its derivatives with respect to beta 1 to beta 0 and beta 1. So L beta 0, the first term here is really dl d beta 0, is the partial derivative of L with respect to beta 0. And the second expression here is the partial derivative of L with respect to beta 1. So these are the derivatives of the binary cross entropy loss function. Now, let me give you an example. So it means that for every given point beta, so I can use my formula for the loss function, the first formula, to compute the loss for that combination of beta 0 and beta 1. And then I can use the second formula, right? So the one with two terms, with L beta 0 and L beta 1, to compute the partial derivatives of my loss function with respect to beta 0 and beta 1. So at every beta 0, beta 1. So this is what it looks like. So we are going to begin at some initial point beta 0, and then we're going to update beta as follows, right? So we are going, so beta 1 is going to be beta 0 minus alpha times dl d beta evaluated at the point beta 0. So beta 2 is going to be beta 2 is going to be beta 1 minus alpha times dl d beta evaluated at the point beta 1, and so on and so forth, right? So we can fill the following table, right? So we are going to begin at some point. So B0, B1 here means beta 0, beta 1. So L0 and L1 are derivatives of L with respect to beta 0 and beta 1. So this is the vector of partial derivatives, and this is L, right? So, and then we take some small value of alpha, and then we basically multiply this by alpha and subtract from beta 0, beta 1, and then this is going to be the new value of beta 0, beta 1. And then we just keep updating this until the value of L hardly changes anymore. And if you look at how the value of L changes, then in the first step, it really dropped a lot. In the second step, again, it dropped a lot. But then it more or less stabilizes, right? So, and then just barely changes. This is what it looks like on a picture. So let me show you a picture. Right, so I'm going to begin at the point minus 3.5 and minus 1. And then, so every time, so here I make some small steps in the direction perpendicular to my level curves of L. So, and then so far, I'm going to just move here. But then at some point, so when I'm making new steps, the value of L hardly changes anymore. I mean, it's not visibly changes, and the value of beta 0 and beta 1, it changes just a little bit, but because of poor resolution of this picture, what we see is that it looks like it is not really changing. But as a matter of fact, this point is moving a little bit to the right or a little bit to the left. It's moving very, very slowly. So I'm trying to move it further, but I cannot really see any visible change. So as a matter of fact here, so the optimal value of beta 0 and beta 1, so the optimal point is probably somewhere here, right? So what happens is that so when we do this gradient descent, so first we very quickly moved to this area, this kind of like a very long hollow on the surface. And so the level here in the bottom of this hollow is almost the same, for different values of beta 0 and beta 1. So it's kind of a very long line, and along this line, so the values of the loss function are almost the same. So they change just a little bit. So which is why when we continue doing these steps of the gradient descent, we can't really see any visible change. But the the value of beta 0 and beta 1 that minimizes the loss function is probably somewhere here. I don't remember where it is, right? So, and then hypothetically, if we just do, I don't know, 1,000 more steps, then we could probably arrive at the minimum point. All right, so now please do the second quiz.